Welcome to Heat Conduction Equation. Understand the core equation behind heat flow. Every subject has a backbone. The heat conduction equation is the backbone of heat transfer. It describes how heat flows inside materials, linking temperature changes to material properties and geometry. This equation is your foundation before diving into steady or transient cases. Once you understand it, you can adapt it to any situation: walls, cylinders, spheres, or even biological tissues. Focus on mastering this core equation. It makes every heat transfer problem easier to handle.
Every great engineer starts with a clear roadmap. In this session, you'll learn to derive the heat conduction equation, understand its time and space dependencies, and apply it in different coordinate systems. You'll practice defining boundary and initial conditions, solving 1D problems, and analyzing cases with internal heat generation. Plus, you'll explore how temperature-dependent conductivity changes your results. Focus on building a complete toolkit. This is the core skill set for solving practical heat transfer problems.
Let's start with the simplest question. Why does heat flow? The answer is temperature gradients. Heat always flows from hot to cold, and we model this using the heat conduction equation. You'll see it applied in 3D problems, steady and unsteady cases, and in 1D simplifications. At the heart of it all is Fourier's law, which directly links heat flow to the temperature gradient. Focus on this principle. It's your starting point for any heat conduction problem, from simple walls to complex 3D systems. 3. Master heat conduction across coordinate systems. Let's structure your understanding with clarity. Heat conduction problems don't come in one shape, they come in many. That's why we study them in 3 coordinate systems. Rectangular coordinates are perfect for plane walls, cylindrical coordinates for pipes and rods, and spherical coordinates for spheres and shells. The mathematics adjusts to fit the geometry. Each coordinate system has its own one-dimensional heat conduction equation. Don't memorize them, understand them. See how the geometry naturally introduces new terms, especially in cylindrical and spherical forms. This is how you simplify complex geometries. Match the equation to the shape, and the rest becomes logical.
4. Master the language of boundaries and initial conditions. Now we move from equations to application. Every heat conduction problem must be anchored by boundary and initial conditions. These are the rules of interaction between the system and its surroundings. We have 4 classic boundary conditions: fixed temperature, fixed heat flux, convection boundaries, and radiation boundaries. You'll see these everywhere, from walls to industrial heat exchangers. And don't forget initial conditions, essential for transient problems. They define how the system starts before it evolves. Remember, boundary and initial conditions are not details. They are defining constraints that make your equations produce meaningful answers.
5. Recognize how solids generate heat internally. Let's move beyond external boundaries and look inside the solid. Many systems generate heat internally. Think of Joule heating in wires, nuclear fuel rods, chemical reactions, or solar radiation in materials. When this happens, we introduce a heat generation term directly into the heat conduction equation. This changes not just the temperature profile, but also the maximum temperature inside the solid. Notice how the temperature peak scales differently in walls, cylinders, and spheres.
Always relate these formulas back to real-world systems, whether it's a cable, a reactor core, or a thermal shield, because heat generation shifts everything in design.
6. Understand heat flow in composite materials. Real systems often involve multiple materials, and this brings in interface conditions. Two key principles always apply. Temperature must be continuous across the interface, and heat flux must be equal on both sides. A great example is a heated wire inside an insulating layer. The wire generates heat, and the heat flows through the ceramic to the surroundings. The interface temperature comes from balancing heat flux. This approach allows you to accurately model multi-material systems without overcomplicating your analysis.
7. Adjust for changing thermal conductivity. Heat conduction isn't always straightforward. Thermal conductivity often varies with temperature. When that happens, we adjust the equation accordingly. A simple linear approximation relates K of T to the baseline K0 and temperature. For practical use, we calculate an average conductivity, especially in problems with large temperature differences. This approach keeps calculations manageable while accounting for real-world material behavior. Always check if your system involves variable K. It can significantly change your heat transfer predictions.
8. See the big picture with the generalized heat conduction equation. Here's the full story. The generalized heat conduction equation combines time dependence, multi-dimensional effects, and internal heat generation all in one powerful expression. From this one equation, you get two important simplifications. Poisson's equation covers steady state with heat generation, and Laplace's equation covers steady state without heat generation. Always start from the general form and simplify it based on your specific case. This approach keeps your analysis structured and avoids common mistakes. 9. Connect theory to real engineering solutions. Heat conduction is everywhere in engineering. From walls and pipes to electronic components, understanding heat flow is essential to prevent failures and optimize performance. You'll also see it in cooling systems, using convection and radiation to control temperatures. Insulation is designed based on conduction theory to reduce heat loss. And in high-stakes environments like nuclear fuel rods or chemical reactors, thermal management becomes a life-critical function. Always ask, how does heat conduction influence the design? Because the answer directly improves your engineering decisions. 10. Wrap up by connecting the key concepts. Let's finish by reinforcing your foundation. You now understand how the heat conduction equation changes with geometry, how boundary and initial conditions guide solutions, and how heat generation reshapes temperature distribution. You've seen how variable thermal conductivity complicates but doesn't overwhelm your analysis. And most importantly, you've connected it all to practical engineering problems, from steady state to transient systems. Keep this big picture in mind. It's the key to solving any heat conduction problem effectively and confidently.